Yeah, so um, one other note that I wanted to make is that there are no quizzes next week because the exam is on Monday. Wait, let me double check that I'm not saying the wrong thing there. Just double check that that's correct. Yeah, so there's no quiz next week, which means that there are Monday discussion sections and there are Tuesday discussion sections. So we're supposed to still have all of them. Um, so I will be in the discussion sections. I'm not sure exactly what I'm going to do. I have a 3 p.m. Monday discussion section. I assume that regardless of what I have planned, there will be some sort of review for the exam, but that'll be pretty last minute. So anyway, just keep your eye on my YouTube channel and yeah, James, I'm gonna I got your message and I'll open that up for you tomorrow. Yeah, if you want to send me a message and tell me like what time you think you could take it, then that's even easier for me, and I'll open it for like an hour for you. Tight. Okay. So yeah, so as I mentioned, this is the most difficult homework of the semester, and of course it's the last one for the quiz, which is like not an ideal situation to be in. But let's go ahead and jump into it. We're going to cover two topics. The first two questions are both on chapter 11, and they both have to do with conservation of angular momentum. So yeah, so we do conservation of angular momentum the same way we do conservation of linear momentum, which is that you just set your initial angular momentum equal to your final angular momentum. Now, as we did with conservation of linear momentum, you know, you have your MV initial is equal to your MV final. In this case, angular momentum is going to be I omega instead of MV. And that's supposed to be an initial. Off to a wonderful start here. So we have I initial omega initial is equal to I final omega final. This equality has to hold for both problem 1 and 2. This is the way you're going to approach it. And for both of these problems, what's going to happen is it's actually going to be the inertia that's going to change. And in both cases, you're going to have a massive putty that gets stuck to some other object. So for our first one, we have a vinyl record where we're given the rotational inertia of the vinyl record explicitly, and we're given the angular speed explicitly. And then a putty is going to get dropped onto the record. So for my problem, my initial rotational inertia is, it's given explicitly in the problem, 5 times 10 to the negative 4. And the only thing that's, well, the omega will change. The only input that I need to change is that I need to relate my final rotational inertia to my initial rotational inertia. So my final rotational inertia will be the rotational inertia of the record, which is still 5 times 10 to the negative 4th. And then I have to add in the rotational inertia of the putty mass. So the putty is going to, it has a mass, and it's going to drop onto the edge of the record, and we're just going to treat it like it's a point mass. So it's going to be an mr squared, and we just add it into the inertia of the record, and that'll be your final inertia. Now, as far as what you plug in for the mass, that's given to me. For mine, it happens to be 0.03, and r, the distance from the center of the record to the putty, since the putty's at the edge, this is the radius of the record. So for me, that's 0.132. And you just plug those in. That'll be your total final inertia. You just plug that in to the left side. You plug your initial inertia here in on the left side. And then your omega initial is given, mine happens to be 5 radians per second. So this is just 5 radians per second. And then your only unknown here is just the final angular velocity of the record, which is what they ask you to find. So yeah, so that's how conservation of angular momentum works. And in problem 2, we're doing a very similar thing. And problem number 2, we have this vertical rod that's swinging and it collides again with a piece of putty. The point of the putty is just that it sticks to the rod. And again, we'll have L initial is equal to L final, which is the same as inertia initial, omega initial is equal to inertia final plus, oh, not plus, times omega final. And yeah, again, I'm given the inertia of the rod explicitly. I'm told that the inertia of the rod, which will be my initial inertia, is 0.1 kilogram meters squared. And the rod's going to swing through those positions, going to collide with this putty, and then the putty's going to get stuck. So my inertia final is, again, this 0.1 plus, again, an mr squared for the little piece of putty. And in this case, again, we're given that the mass of the putty is 0.12 kilograms in my case. And the distance now is, again, the distance from the rotation axis to the putty. And the way that the picture is drawn, that just happens to be the length of the rod. So for my problem, the length of the rod is 0.6 meters. So I would plug that in for my r and square it. And those two multiplied together will give you the inertia of the putty. You just add it in. And then just as we do in the last problem, you'll plug in this whole thing for your final inertia. You'll plug in just the 0.1 for the initial inertia, and they will give us that the angular speed just before the collision is, in my case, 4 radians per second. So we plug that in for omega initial, and again, solve for omega final. As far as exam problems to be aware of that deal with conservation of angular momentum, you know, one would be an instance where they wouldn't give you a number here. They would give you just like a variable and maybe ask you to solve for that variable. So you'd have like some I constant that you're solving for, and that would be your I initial, and then your I final would be whatever that constant I is plus the adjustment for the putty. And then you could think about doing the algebra to sort of back out that I and isolate it. But yeah, so as long as you have these two problems down, these are the conservation of angular momentum problems that you need to be most sort of prepared for. And those are the first 2 questions in the homework. Those are chapter 12. And those are chapter 11 rather. And now we'll move into chapter 12. And chapter 12 is chapter 12 is the most difficult chapter you're going to do in this class. So chapter 12 is sort of building on everything that we've done so far. Specifically, we are going back to this case of static equilibrium. So we've had equilibrium problems back when we did forces. We maybe didn't explicitly call them equilibrium problems, but an equilibrium problem is a case where when you sum the forces in the x and you sum the forces in the y, they're both equal to 0 because the object isn't accelerating. So that's an equilibrium problem. If you are in static equilibrium, that also means that the object is not moving. So you can think of, there's a ton of engineering examples. And in fact, you're going to take an entire class. If you're in engineering, you're going to take an entire class. I think you're like qualified for it after you finish this one, called statics, which is just concerned with doing these types of problems. And you'll be able to actually give these problems like the sort of attention that they deserve. Unfortunately, in this class, we just only spend a week on them. But you know, common examples are like you have a wall or something, and there's, you know, a support beam that's leaned up against the wall, and you can look at all the forces and stuff that are going on here. So you have like the weight of the beam, you have a normal force with the ground, you have a normal force with the wall, you have a force of friction with the wall, you have a force of friction with the beam. And so you can do your forces in the x and your forces in the y and set all these equal. The other thing that we can do now, and the reason why this chapter comes now, is because we can also sum the torques and set that equal to 0. And so we're going to be doing r times f for a lot of these problems. And that's going to require one thing that you'll have to do is set your pivot point. Now, the object isn't actually rotating. So we don't have a predetermined pivot around which the object is rotating. You then have the freedom to sort of set that. So generally you'll take a point where there are a lot of forces that are being applied, and you'll set a pivot there, and then these two forces will exert no torques around that point. So you just need the torque of this force and these two. For example, I'm just sort of generalizing here the types of problems that we're going to be doing. But the point is that we're going to be doing a lot of like large system of equations problems, and trying to sort of flex these tools. But these are the tools that are in our toolbox, and this is how we're going to set up a lot of these problems. And yeah, so yeah, just as a reminder, when we're doing the torque of some given force F, the calculation that we actually need to perform for each torque is that it'll either be plus or minus, depending if it's a positive or negative angle that it's rotating through. And then we have R, which is the distance from the pivot point that we choose up to the force, whatever that R happens to be, times the magnitude of the force itself, times the sine of the angle phi, where phi there is taken to be the angle between the force and the R vector, which is, in the problem with the beam, it would be the angle between this force of gravity downward and the beam itself. This would be our angle phi that we'd be investigating right here. Oops. Phi would be right in there. Okay, yeah, and then as just, again, one more reminder for the sign convention, when we have a counterclockwise rotation, that's going to be a positive torque. And when the force causes a clockwise rotation, that's going to be a negative torque. So I think that about covers the rules, and how we're going to approach these. But we can go ahead and start working through some. The first one, problem number 3, starts us off with a little bit of a baby step. We have these 8 people sitting on a seesaw, and we're given their weights, and we're also given the distance from the fulcrum in the middle, which is just, in this case, we're sort of setting our pivot point automatically. And I'm not going to draw all 8 people, but we have person 1, 2, 3, 4, 5, 6, 7, 8. And yeah, and so these all correspond to certain weights. 220, 330, 440, and 560. And they're mirror images, so we also have 560, 440, 330, 220. And the distances are also the same, 1 meter, 2 meters, 3 meters, 4 meters. So this is the weight, and this is the distance, which we'll go ahead and just call R, because that's how we're going to use it. And yeah, so the first thing they do is they ask us to, well, they ask us to find the largest torque, and then they give us 2 different rotation axes. So the first thing I'm going to do, before I talk about the rotation axis and how we determine which person has the largest torque given the rotation axis, first thing I'm going to do is I'm going to go ahead and calculate my torques. So for each torque, it'll just be R times F, where R comes from this, from the second line. Okay, this R is going to come from here, and my F is just my weight, which will come from right here. So I'm just multiplying these numbers together. 4 times 220 gives me 880. 330 times 3 is going to give me 990. 440 times 2 is again 880. 560 times 1 is 560. Okay, so which one of these is the maximum magnitude of a torque? Clearly it's going to be 3. I'm sorry, this is actually person number 2. And since these are mirror images, that means that person number 7 will also have the same magnitude. It'll also be 990 Newton meters. So that solves the magnitude problem. Of course, they give us 2 different fulcrum directions, which is a little bit strange. In the first one, they say that the fulcrum is coming out of the page. Oh no. was supposed to be a pencil. Okay, cool. Fulcrum coming out of the page looks like this. In this case, we can use something called the right-hand rule, which tells us that a positive torque would be anything that rotates us in this direction. And so in this case, it would be the weight on number 2, which points downward, that is rotating us in a counterclockwise direction. So that means that number 2, for the fulcrum out of the page case, has the largest torque. Person number 7 in this case, remember, still has 990 Newton meters of torque, but in this case, since person number 7 has a weight that is directed downward on the right side of the fulcrum, that actually goes in the opposite direction of the counterclockwise that we've assigned here, based on the fulcrum being out of the page. And that means that person number 7's torque, when the fulcrum is out of the page, is negative 990 Newton meters. It's a little bit of a technicality. This isn't really going to build as we go forward. We're just always going to take the fulcrum to be out of the page for the rest of the problems that we do. But for this one, we just need to understand that difference. For the second part, they ask us instead to have the fulcrum into the page. Again, we could do this thing called the right-hand rule. Now we stick our thumb into the page and curl around, and that tells us that now clockwise is the positive direction. Again, clockwise is never going to be the positive direction for the rest of this assignment, so forget that after this problem. But the point is just that the fulcrum happens to be in the page. Now the weight of person 2 is providing a negative torque because it goes against the clockwise direction, and it's the weight of person number 7, which is providing the positive 990 Newton meters of torque. So that's just the two problems. Again, just get this problem right and then forget that sign convention. Going forward, it'll just be counterclockwise positive, clockwise negative, and we're not even going to talk anymore about the direction of the fulcrum. Okay, so problem number 4 is actually just a static forces problem. Setup for problem number 4 is you have a car that's stuck in the mud, and this guy is going to tie a rope to the front of the car and then tie that rope around a pole, and then he's going to push horizontally. So here's the car's on the left, that's the pole. The rope is strung from the car to the pole, but the guy is pushing on the rope so that there's like a little bit of a bend in the rope, and that's his applied force right there. And what do we ask for? I think we're asked for the magnitude of the force on the car from the rope. So the magnitude of the force on the car from the rope, since it is a rope, that's still a tension. And but what's going on here is that the tension is also going to exist at this point where the guy is pushing. And it's just at a slight angle, but you essentially have these two different tensions right here. And yeah, so we can zoom in a little bit and look at this angle that's being made in the rope. And we can relate that angle to the tension. So this guy's applied force right there is countering the y component of each of these tension forces. So each of the tensions is going to have a y component. There will be 2 of them. And since they are opposite this little angle theta that we've defined, that means that they would each be t times the sine of theta. So together, well, we'd have 2 of them. So it'd be 2 times t times the sine of the angle theta that we've defined. And then the way that we actually find the magnitude of that angle is to use the distances that are given in the problem. So we have that the rope has been displaced. In my case, it's 0.2 meters. And we're told that the distance from the front bumper to utility pole is, in my case, 20 meters. So this length here would be 20 on 2 because it's only half the rope. He's pushing on the midway point of the rope. You'd have 20 divided by 2 on this side, and then you have 20 divided by 2 on the other side as well. Cool, and then we can use these to define that sine of theta. it'll just be the opposite of the hypotenuse, 0.2 over 20 on 2, which will be um, uh, uh, mind is blanking. It's going to be a very small ratio, 0.4 on 20, which is 0.04 on 2, which is 0.02. I think I just did that right. You can check my work if you want. Point is that we just need a value for this ratio because this is the sine theta. So then when we go to sum the forces in the y direction about that point, upward we have the applied force F, minus downward we have 2t sine theta. And since we are in equilibrium, this will be equal to 0. And then we just solve from here. Ultimately, what we're solving for, we're looking for the tension. So solve for the tension here. You have that the tension will be equal to F over 2 sine of theta. And we're given the applied force. So we plug that in on the top. And then we just plug in the value for sine theta that we found in the blue here on the bottom. And that will give you your tension in the rope. Okay. So we didn't actually have to use torques there. Forces are still on the table. Ultimately, I think for most of the rest of these problems, we're going to have to do both forces and torques for basically every single one. So problem number 5, we have, this is one of the flying circus of physics problems, which, as you may have learned at this point in the semester, just basically means an incredibly convoluted setup that makes approaching the problem very difficult and confusing. This is a rock climber, which, okay, fine, kind of annoying, right? And there's like a gap. This guy has his feet pushed against the wall and he's pulling on a different part of the wall, and it's just an incredibly confusing setup. But let's try and simplify the picture that we're looking at as best as we can. This is probably an awful problem to be our first problem that we're doing with torques, but we're going to go ahead and try and make it work if we can. So, all right, so let's have our gap between the wall. This is W, not omega. Should make that a W. This is some width W. And the guy is going to attach his hands right here, and he's going to push off with his feet down here. And the distance between those is H. And then his actual body is going to be somewhere between there, but we just need his center of mass. They put his center of mass right here, and that center of mass is a distance of D away from the wall. Okay, so let's talk about the forces that are involved in this problem. So the first one, at the center of mass, you're going to have your weight, or your force of gravity. That'll be directed downward, so we're good with that. Where the guy is pulling on the wall, what are the forces on his hands there? The first is that there will be a normal force. He's pulling in this direction. So that means that there is a normal force counteracting that, which we'll go ahead and call normal force 1. Also there, if that wall were made of ice, his hands would go slipping down. The reason why his hands don't go slipping down is because there's a force of friction, which we'll call friction 1. At the other point in the lower right corner, where his feet are pushing up against the wall, now his feet are pushing in this direction. As his feet are pushing into the wall, there has to be a normal force opposing it. We'll call that N2. And then again, because he is not sliding down the wall because the wall is not made of ice, there's also a friction there, which we will call F2, force of friction 2. Let me see if I can give us a little bit more space here. That's going to be friction 2. Let me put that distance H back on there because we're going to need it in just a second. Okay. So this is all the forces involved, and these are all the forces on the guy himself. And we're given some coefficients of frictions, we're given all these distances and all that stuff. Well, the first thing that I generally do is I start by doing the forces. Yeah, Michael, the friction points upward because that's the thing that's holding you up when you're holding onto a rock, especially when we're holding horizontally the way he is. He's applying both of his forces with his hands and his feet horizontally. It's the friction that's keeping him from sliding down. So since it's keeping you from sliding down, that friction has to be pointed upward. Okay, so yeah, so start by summing the forces in both the x and the y and see what comes out. Luckily, we are in static equilibrium, which means that when we sum our forces, it's going to be equal to 0. We just need to determine what is positive, what is negative. In our positive x direction, the only force in the positive x direction is n1, pointing to the right. And in the negative x direction, the only force is n2. So n1 minus n2 is equal to 0. And that gives us right away that n1 has to be equal to n2. Not necessarily always the case when you have two normal forces. In this case, it happens to be true, and that'll be maybe a beneficial thing to know. Next up, we'll sum the forces in the y direction. Acting upward in the y direction, we have our force of friction 1 and force of friction 2, and then acting downward is the weight. So that's F1 up plus F2 up minus the weight down, and those will be equal to 0. So maybe to rearrange this just a little bit, we have F1 plus F2 is equal to W. In other words, it's the two forces of friction that are supporting the weight. So to go back to Michael's question, there's an actual physical explanation. We're not ignoring the forces of him pushing or pulling on the wall. That's what the friction in the normal force is. We have labeled just the forces on the person himself. We don't care about the force that he's exerting on the wall because we are trying to keep that man up in the air. So we're looking at the forces on the man. We don't care about how hard he's pushing on the wall. If you wanted to see if the wall was going to break or something like that, then you'd look at the wall itself. Cool. All right. So we have these two relationships. Now we're not really any closer to solving the problem. Ultimately, by the way, I guess I should say, because the problem asks us to find the horizontal pull by the hands and push by the feet. Those are just the same as these two normal forces. So once we solve for them, that will be the answer to part A, and then we can solve for H as well for part B. But in order to solve this problem from here, we have these two relationships. This is clearly not enough for us to finish the problem. So the last thing that we're going to need to do is summing the torques. And unfortunately, this is the first one, the first problem that we're doing where we are summing up the torques. Oh, I should actually point out, we can solve a little bit further here. We can actually go ahead and solve part A. Because we have this relationship with the force of frictions and the weight. This tells us that mu1 times n1 plus mu2 times n2 is equal to W. And then we know that n1 is equal to n2. Since n1 is equal to n2, this means that mu1 plus mu2 times whatever the normal force is would be equal to the weight. And then the only unknown here is just the normal force. So we have that the normal force is equal to the weight over mu1 plus mu2. Yeah, so, and I can tell that I didn't explain this because this is the second time that the same question has been asked. So let me try and slow it down real quick and explain why we are solving for these forces and not solving for the push or the pull. When the guy, let's just say we have a wall. Here's a wall. And let's say that there's a person who's casually leaning against the wall. When I casually lean against the wall, there's some amount of my weight that I'm sort of supporting with the wall, right? So that is my push force that I'm pushing against the wall. That force would cause me to go tumbling through the wall and fall to the ground if it were not for a force from the wall pushing back on me that is equal and opposite. That's the reaction force. That force is called the normal force. These two have to be equal. So if I'm asked to find the force with which I push on the wall when I lean on it, that's the exact same thing as finding the normal force that the wall pushes back on me with. So in the case of this problem, where the hands are up here at the top, the guy is pulling inward with some force that we're asked to solve for. That's got to be the same, equal and opposite to the normal force that the wall pushes back outward on the guy with. And the same thing is happening down here where the feet are pushing in this direction and the normal force is pushing back against the feet. So to solve for the normal forces is the same thing as solving for the force with which I push or pull. The push or pull is just a weird way of phrasing it. They could have just asked you to solve for the normal force to be the same thing. At any rate, once we solve our force relationships here and do a little bit of solving, we can find this general expression for both normal forces. And now we know the values of each of the normal forces. Cool. All right. Okay. So that's part A. Part B, what are we looking to solve for in part B? In part B, we are looking for, the value of H itself. So here is where we're going to have to actually do the torque calculation, keeping in mind that we now know the normal forces, and of course we know the force of frictions then as well, because force of friction is just mu times the normal force. In order to calculate the torques, we first of all need to define a pivot point. And we have a little bit of freedom in defining our pivot point. Ultimately, we want that pivot to relate back to the height h in some way. So we want to be measuring our forces and the distance of our forces relative to h. And the most sort of common sense place to assign a pivot point is going to be at one of the points with the frictions. Here's why. At the point where you have friction and a normal force. For instance, down here, we have both friction and a normal force that is applied there. Since the torque is r, the radial vector to the force times the force, if we can make r equal to 0, then the torque from those forces is equal to 0. So for instance, by setting my pivot point here, my torques from the force of friction 2 and from the normal force 2 will be 0. So what I can do then is I can calculate the torques that are just due to the other three forces here. So I'm going to go ahead and sum my torques about this point down here. Force friction 2, normal force 2 have no torque. I just need to find the torque due to the weight and then due to force friction 1 and normal force 1. So here's how that's going to happen. Let's start with the weight. The weight is going to be the easiest one. For the weight, what I can do is I could draw a straight line from my pivot point up to the center of mass where the weight is applied. And then my weight would be at some angle phi. So when I do sine of phi, then I would find some angle there, and I can relate that angle back to the distances and so on and so forth. The other thing, this is something that I did last week when I was doing angular momentum, where I just took the radial component that was perpendicular to the force. In that case, that would be this radial component here. This radial component, if you remember last week, we had like the angular momentum is equal to m r perpendicular times v, and we let r just be the distance along the ground. That was some delta x. We can do a similar thing here where instead of doing rf sine phi, this will be the same thing as the r that is perpendicular to the force as measured from the pivot point. So in this case, the r that runs perpendicularly to the weight force will just be a horizontal line, and that horizontal line will have a length of d plus w. The last thing that we need to do then is look at, well, let's go ahead and write that down. So when I do rf, our r perpendicular times the force for that weight, the perpendicular distance is d plus w, as I just said. And then we have the weight, which is mg. So that's my RF. The last thing we need to do is determine if that's going to be a positive or negative torque. So just take that weight and see, is that rotating us clockwise or counterclockwise around the pivot point? That looks to be counterclockwise to me, so that will be a positive torque. So again, this is my R perpendicular, the component of the radial vector that is perpendicular to the force, times the force itself. Okay, the other two forces that I have are the next one we could do, I guess, is the normal force. Let's do that one. For the normal force, I will, again, just draw a straight line. I again want to do the component of the radial vector that is perpendicular to the normal force. And you'll notice that this r right here is just equal to h. So the torque there, when I do the r perpendicular times the force, will be h times normal force 1. Be h times n1. And then the last thing is we need to determine if that's positive or negative. Normal force 1 gives us clockwise rotation around the pivot. So that would be a negative torque. That's a plus sign, James, just not a very good one. That's d plus w. This d here plus this w here. Okay. The last force that we need to assign a torque to is the friction component 1. Put that wall back. No. Cool. Friction component 1. Now in this case, this force is directed upward. The radial vector that would be perpendicular to frictional force 1 would extend like this. And so the distance there is going to be just w. So again, when I'm doing r perpendicular times the force, my r perpendicular is going to have a length of just w. So I'm running out of room a little bit here, but that would be w times force of friction 1. And then we need to determine if this is going to be positive or negative. Apply friction force 1 and see the direction of the rotation. And you'll see that it is a clockwise rotation. So that's going to be, again, a negative torque. Why is, I'm not sure which one, the torque is negative because that force, a very straightforward way to determine if the torque due to a force is positive or negative is to draw a line from the pivot point to the force and then just see if the circle goes clockwise or counterclockwise. So for normal force 1, that circle goes clockwise, that's a negative torque. For force of friction 1, that circle goes clockwise, so that's a negative torque. And that's where these two negative signs both came from. For the weight, the reason why that one is positive is if I draw a line directly out to the weight and then just rotate that weight around, that's a counterclockwise rotation, so that's a positive torque. Okay, cool. Yes, okay, this is all one line, by the way. I've just run out of room, and this is all going to be equal to 0. Again, this is an awful first problem to do. In retrospect, I probably should have done a later one first, but they're honestly not going to get much better than this. All right, so ultimately in this problem, yeah, we wanted to solve for h. Now, we've already found the normal force in part 1, and we just need to replace our force of friction. If we solve for h here, we'll get that h is equal to d plus w times mg minus w times force of friction 1 divided by normal force 1. And then the last thing that we just need to do is substitute in for the force of friction 1 here, mu1 times normal force 1. And then I believe we're given w, and we've got mg, and we have d as well. I think those are all, yeah, those are all constants. So you have everything that you need there to plug in. Okay, so I'm just gonna keep going through. If you're having trouble with this one, yeah. So N1 is the normal force where the hands are, Charlotte, up here. We solved all the way back in part 1. We did some of the forces of the x direction. We found that normal force 1 and normal force 2 are the same. So you could just call them normal force generally. That won't always be the case, but that was for this problem. And yeah, if you're looking at this problem and you're not really sure what's going on and you feel like you have no hope of ever solving this on your own in the wild, you are not alone. I think that's most people sitting in this, watching this video right now should probably be confused at this point. Would we be able to solve it with the pivot at F1 or N1? Yes. Yeah. So we could talk just briefly about how that torque equation would be set up if we were to set up the pivot up at the top here. In that case, our perpendicular components for when we do the r perpendicular times f. So there's two things here, right? We have to do the sine, and then we also need the perpendicular distance. So for the weight, the perpendicular distance would be measured here, and that perpendicular distance is just d. And then for F2, the perpendicular distance would be right here, which will be equal to W. And for N2, the perpendicular distance would be right here, which is just the same as H. So you'd end up with an identical equation, and you should get the same answer. So that's also a way to check your answer. Let's see. Yeah, Michael, I would say that the hardest part is the torques. We will hopefully get to some problems where we don't have to be doing this weird sort of operation to find r perpendicular. I think for the next problem, we're going to have to do something funky as well, though. It's just unfortunate that that the problems on this homework are just like right off the bat wildly difficult instead of sort of building towards something and just having like a few difficult ones at the end. Okay, so next problem, we've got a wheel. And we're trying to get this wheel up a step. And the step has a height of h, and we're applying a force to the wheel to get it up that step. And we're told the wheel has mass. So first thing I would do is say, okay, that means that I'm going to have some weight downward. So I've at least got two forces on the wheel. There's the applied force to the right, and there's the weight downward. So far, so good. Nothing crazy going on. Now, while the wheel is rolling along the ground, there'd be a normal force upward, and there'd be a force of friction. But what we're doing as we climb this step is we're applying the force until the wheel starts to climb up the step. So we're looking at the point when the bottom of the wheel is no longer in contact with the ground. The only point of contact is going to be with the step over here, and you'd have some force from the step, and that would be technically a normal force, and it's going to point technically perpendicularly to the point of contact, so it's going to point radially inward along the wheel. So what we need to do is sum our forces in some way, and ultimately, what are we even solving for? I think we're solving for the like minimum applied force that will get us, yeah, magnitude of the force required to raise the wheel. So we're solving for F eventually. And okay, so we can approach this a few different ways. First thing I'm going to do is I'm going to zoom in on the geometry here and see what kind of information we can get out of the geometry. So here's the center of my wheel. The wheel looks like this, and then we have the ledge over here, which has a height of h. And we know that this distance right here would be the radius of the wheel. And if I wanted to generate a right triangle, I might be getting ahead of myself. But ultimately, what I know is that the normal force is going to be applied along that radius. So I'm going to want something to do with the angles here and the distances, and the height is going to matter. So this is a radius r, and this distance will be r minus h. And this will generate a right triangle. And what I've done here is I've given myself a way to split this normal force up into two components, into an x and y component. And we'll call this n sub y and n sub x for now. We'll come back to the geometry in just a second. The reason why I want x and y components of the normal force, though, is because I want to sum the force in the x and y direction. In the x direction, I have my applied force F minus the x component of the normal force is equal to 0. Or to just do this in one step, we know that the applied force has to be equal to the x component of the normal force. When I sum the forces in the y direction, I have the y component of the normal force upward minus the weight downward, that's equal to 0. Or just in other words, the weight has to be equal to the y component of the normal force. So I know that these two things have to be true. And now ultimately I want to find the applied force, which means I'm going to need to relate the normal force back to sort of the geometry of this problem. And so I'm going to go back to this triangle. I know that I can define this angle theta. And I know that sine of theta will be the opposite over the hypotenuse, and cosine will be the adjacent, which I haven't calculated, but I can, over the hypotenuse. So let's go ahead and make that substitution. So my first equation will become F equals the normal force, whatever it happens to be, times the cosine of the angle theta. My second equation will become that the weight is equal to n times the sine of that angle theta. Now, sine and cosine can come from the geometry of the picture. I'm good with that. I know I can do it. I haven't done it yet. I know I can. One thing that I know for sure is that I do not know any information about the normal force. But one thing that I do know is that the two forces have to be related in this way. Sorry, I just lost my train of thought. I don't know the normal force. I know that I want to get rid of the normal force from these two equations. I also know that sine over cosine is tangent. So immediately in my head, when I'm looking at these two equations, I'm thinking, if I could divide the bottom equation by the top equation, sine over cosine would give me tangent, and my normal forces would cancel out. So let's go ahead and do that division. I wish I had written them in a different order. But if I do that division, then what do I get? Dividing the top one by the bottom one, I end up with W over F on the left side, because it's W divided by F. And on the right side, my ends cancel, and I have sine over cosine, which is tangent of theta. So I've done a little bit of work here, a little bit of elbow grease to at least eliminate the normal force. And now I have a relationship between the applied force that I'm looking for, the weight which I'm given in the problem, and the geometry of the wheel itself in that tangent of theta. So the last thing that I would need to do in order to solve for that applied force is I need to find an expression for the tangent of theta. So I'm going to clear up a little bit of space up here and redraw my triangle. Here's my angle theta. This is r. This is r minus h. I'm just copying down this guy down here. I'm just making it a little less cluttered. Using the Pythagorean theorem then, a squared plus b squared equals c squared, I know that my last leg here would be the square root of r squared minus r minus h squared. And I can simplify that a little bit. Squaring the binomial there will give me an r squared minus 2rh plus h squared. So I have that this is the square root of r squared minus r squared minus 2rh. No. 2rh plus h squared. R squared minus an r squared. Those will cancel and we'll have 2rh minus h squared. And then finally, I can write down the tangent of theta. Tangent of theta is going to be the opposite over the adjacent. My opposite is r minus h. And my adjacent is square root of 2rh minus h squared. And I know that this right here has to be equal to w on f, and then I can solve for f from there. So I guess we didn't even really use torques here. This problem has been a homework problem for at least as long as I've been around this class. And this has always been, I think, the most straightforward way to solve this problem. It's not a very intuitive solution, and it doesn't really build any intuition or anything like that. But it is a problem every year. I'm gonna go ahead and keep moving. I think the next problem is the first one that is actually actually builds some intuition and helps you sort of start to learn how to approach these problems. I didn't TA this class. I've only been a grad. This is my 6th year as a grad student. Only my 6th year as a grad student. But I first taught. I lectured for this class at one of the off-campus tutoring companies for the first time in, I think it was summer of 2012. I was still an undergrad, and I have no idea how I got that job. I probably wasn't qualified for it at the time, but that was the first time that I taught this class. And a lot of these homework problems have not changed, and like the structure of the class hasn't really changed in all that time either. And it was pretty constant at the time. Yeah, turns out you can just stick around here forever. Okay, so this problem is the first problem that I think is actually this is one that hopefully you'll take something away from. You have a plank, and there's like a hinge sort of mechanism for the plank. There's a rope tied to the end of the plank. This is a very common setup. The rope is at an angle, there's a tension in the rope, and they label the angle. This setup comes up again and again, especially on exam problems. Now for the homework problem, what we're going to do is we're going to set a little box right here that is a distance of x away from the wall, but that's not always the setup. But the general approach is going to be the same every time. So first things I like to do is label all of my forces. And the forces here are going to be on the plank. So I have, as I mentioned, the tension in the rope that is tied to the end of the plank. The plank itself has a weight, and that will be at the center of the plank. So call that W sub P for weight of the plank. And then there's a block, and the block is also going to have its own weight that will be applied at its center of mass. So call that the weight of the block. And then there is the hinge at the wall, and that hinge is going to apply two different forces, similar to the mountain climber problem. So there is the normal force of the wall that's going to push outward along the plank perpendicular to the wall. And then there's also the force of the hinge itself. So there's some screws in that hinge that are screwing the plank into the wall, and that's a vertical support force that prevents the plank from sliding down the wall. Okay, so these are all of our forces, and we can start by summing the forces in the x and the y, as we've done however many times at this point in the semester. And start in the positive x direction. Positive x direction, I just have my normal force from the wall that's pointing in the rightward direction. That'll be a positive force. And then I have to subtract a component of this tension. It'll be T times the cosine of this angle theta. That's just the x component. So minus T cosine theta. And we are in static equilibrium, so this is 0. And this also tells us that the normal force is just equal to the tension times the cosine of the angle theta. Doing a similar thing with the summing of the forces in the y direction. Acting upward, we have our hinge force, which is just directed straight upwards, F sub h. Also acting upward is a component of this tension. It'll be positive, T sine of theta. And then acting downward are our two weights. So we have minus the weight of the block minus the weight of the plank. And together this will all be equal to 0. And we could rewrite this if we wanted to as F hinge plus T sine theta has to be equal to weight block plus weight plank. Okay, now what are we looking for? We are looking for the distance before the wire breaks given a maximum tension. So we don't have anything about distance in these equations. And then with the block there, we want to find the horizontal and vertical components of the force on the bar from the hinge. So the horizontal component will be this guy right here. We just need to find the tension and the angle. And we're actually given that the maximum tension is, in my problem, 400 newtons, and we're given the angle as 37. So you could actually plug those in, and that would be part B, your answer for that one. For the vertical component is going to be this F sub h right here. And in order to find that, well, let's see, we have T sine theta. We can plug in the givens for tension and theta to find that. And then we are also given these two weights. So you can also go ahead and solve for the hinge force. So that would be part C, would come from this equation. But the one that we need to solve for, part A, which part A asks us for the distance x. And in order to find that distance x, you might be able to surmise at this point, surmise, is that the right word? You may be able to guess that in order to find anything about a distance and relate to forces, that's going to have to be torques. Hopefully that intuition is there. Yeah, F sub h is just the vertical component of the hinge force. Yep. Okay, so yeah, so for part A, we have to go ahead and do our torque calculation, our Newton's second law for rotation. And as I've talked a little bit about, um, the advantage that you have when you're in static equilibrium is that you can place your pivot point wherever you want. And I usually pick a pivot point where the most forces are being applied, because then the torques from those forces is zero. So in this case, I have the hinge force and the normal force over here. If I, why did it go away? If I were to set my pivot there, then the torque from the hinge, the torque from the normal force would be zero, and I only need to calculate the torque from these other three forces. So we can go ahead and do that real quick. We can just check the signs. That tension is going to cause a counterclockwise rotation, so the tension is going to have a positive torque. The weight, both of them, will cause clockwise rotation, so those will both be negative torques. So let's go ahead and do it. Sum the torques about the hinge. And my general recommendation is to start at your pivot point and move outward. And as you encounter forces, that's when you decide to add or subtract the R times F for those forces. And remember, it's RF sine phi. So on our way down, first one that we hit is the weight of the block. Now, I just mentioned that that's going to be negative. The distance from the hinge to that block is the X that we're solving for. So that's our R in the RF. And then the force is the weight of the block. Okay. And then sine phi, but since it's a perpendicular force, phi is 90, so sine of phi is 1. So we don't need to worry about that. Keep traveling out. The next force that we encounter is the weight of the plank. This is also going to be a negative. The distance here, since the plank is uniformly distributed, the weight of the plank will be right at the middle of the plank. So the distance from the hinge to the middle of the plank is the length of the plank divided by 2, L over 2. And then we multiply by the weight of the plank. And then sine of phi is sine of 90, which is 1. And then we keep going all the way out to the end. That's where we encounter the rope with its tension. That's going to be a positive torque. The distance from one end of the plank to the other is the length of the plank. And then we have the force itself, which is the tension T. And then we have sine of phi, where phi is the angle between the force and the radial vector, which happens to be this theta in this problem. So that'll be sine of theta. And then this is all equal to 0. Everything that we have in this equation is a known except for x, which is the distance that we're solving for. So yeah, so we just need to solve for x, and it will be something like, do this in my head, L t sine theta minus L on 2 times W sub p divided by W sub b. No, not like this. W sub b. Cool. Anyway, I'm sure you can do that isolation yourself, but that is the way that the solution works. Most important thing here, though, is knowing how to set up this torque equation. And knowing how to set up the torque equation for the beam problem, especially a beam where you have different forces involved, is a very important tool for the exam. Oh, okay. Problem number 8. Yeah, okay. Problem number 8, we have a vertical beam now. So we have a floor. Now our beam is vertical. There's a hinge still at the bottom, and there's a cable. And now we're going to apply a force right here. And we're applying the force at some unknown distance, which they call y. And we get a figure for the tension. And the horizontal force of the beam. Okay. So to start, as I did in the last problem, let's label our forces on the beam. We have a tension, obviously, and we're given that this rope is at an angle. Oh no, no. This rope is at an angle theta. But the tension force, yeah, we'll rely on that angle theta. And then we have we don't have a weight, but we do have this hinge. And what's going to happen with the hinge is there will be a normal force that will point perpendicularly. And then there will also be a hinge force. Now, we don't know necessarily the direction of the hinge force, but they do give us, based on the graph that's shown, it appears that hinge force is positive. So let's go ahead and indicate that hinge force is going in the positive x direction. And yeah, so this is going to be all of the forces. I suppose there's also a weight somewhere in here. Vertical uniform beam. Yeah, there'd also be a weight at some point that would point downward from the center. I'm not sure exactly where to set it. I'm going to do it like this. We're ultimately not going to be concerned with that weight, and we're going to attempt to ignore it. Luckily, it points along the beam, so for any torque calculation, when we do sine of phi would be 0, and the torque from that weight would be 0. Same thing will be true for the normal force. Now, for the calculation here, we could do the sum of the forces in the x direction. You have the hinge force plus the applied force will be equal to, well, let me actually write that down. You don't need to write this down, but what you get from summing the forces in the x direction is that the hinge force plus the applied force will be equal to t times the cosine of the angle theta. That's not going to be super useful to us, but well, we can write that down. We may need that at some point. What I will say is that by summing the forces in the y direction with the weight and the normal force and all that stuff, that will not be as useful to us. What we do definitely want to do is we want to sum the torques. And when we go to sum the torques, again, we want to take advantage of the fact that the most forces occur at the pivot point. So we're going to want to sum the torques about the pivot point. So when I sum the torques about the pivot point, the torque from the hinge force, torque from the normal force, those go away. The weight is parallel to the beam itself, so that has no torque. The only two forces that exert torque around the hinge are the applied force pulling to the right and the tension that are pulling to the left. So which one will be positive? That will be the tension, because that's giving us a counterclockwise rotation around the hinge. So that tension is located at a distance L, and it'd be tension. And then we need to do RF sine phi, where phi is this angle here. Sine of phi is the same thing as sine of 90 minus theta. So I'm using some trig identities here. I'm going kind of fast here. This is our phi angle right here. We know because this is a right triangle, that phi plus theta have to be equal to 90. So I need sine of phi right here. But sine of phi is going to be the same thing as cosine of theta because these angles are complementary. Okay, so I'm going to write this as cosine of theta, but I just need to mention that this is still the same thing as sine of that angle phi between the tension and the beam itself. The negative torque is going to come from the applied force, which is giving us a clockwise rotation. The distance from the hinge to the applied force is this y value right here. So I have minus y times the applied force. And the sine of phi in this case, because the angle between the applied force and the beam is 90 degrees, sine of 90 is 1. So we just have a 1 there, and this will all be equal to 0. Rearranging this just a little bit, we have LT cosine of theta is equal to y times f sub a. And looking at the equation that I have up above, I see that I also have a t cosine theta there as well. So ultimately, I'd probably like to relate those two. And I know that I do have a relationship between the um, the tension and y over L. I know that I have a graph. So the graph in part B gives me y over L versus the tension. Now, the graph's maybe not super great as far as reading values off of it. Maybe I don't know what information I'm going to get here. But what I do know is that my slope is always y over x. That's always the case. In this case, my y is the tension and my x is y on L. So the slope of the graph for part B, or the graph that is labeled B, the slope of the graph is going to be tension divided by y on L. So by rearranging this equation here, I can divide by y, and I'll have LT cosine theta on y is equal to the applied force. And I know that the slope of my graph could give me a value for t divided by y on L, but t over y on L is just the same thing as if I reciprocate the denominator, LT on y. So notice I have LT on y right here. That means that this will be the slope from part B. So f sub a is equal to cosine theta. What is that? Cosine of theta. Am I really? Okay. Times the slope from my graph that is labeled B. And again, that's just because that slope is t on y on L, and I have L on LT on y, which is identical. And let's see. Okay, so what does that give us? Ultimately, we want to find the angle theta. I can read the slope off of the graph, and I know that the applied force is not given to me, so that doesn't necessarily give me any sort of value. However, I do know that I have this equation, which also will relate the applied force and the hinge force and things. So the actual force that I'm given is that I'm given the tension, and that is the only number I think that I'm given in the problem, aside from the slopes. But I am ultimately where else does LT on cosine? Let's see. Okay, let me write down these equations that I have real quick. I have this equation and this one. f sub h plus f sub a is equal to t cosine theta. And the second equation was LT cosine theta equals y times f sub a. LT cosine theta equals y times f sub a. And from the graphs, I have a relationship of t on y over L is equal to the slope of graph B. And the second graph gives us that the ratio of f sub h to y on L, that'll be the slope of graph C. And ultimately, I want to find theta. I am also given, my last given is that I'm given the scale of the tension axis. Okay. So how do I combine these together? Oh, okay, I see. LT on y is equal to, okay, so it's this is what I was just working on. LT on y is equal to f sub a on cosine theta. So this will give us a value for f sub a on cosine theta. We can read directly off of the first graph, as I just had. And then from the second graph, we can substitute in for cosine of theta. We can substitute in, rearranging this equation, tells us that cosine of theta is equal to f sub a times y on LT. This is just a rearrangement of the equation that I've just written. And I'm going to go ahead and substitute that in to my equation that came from summing the forces in the x direction. So I have f sub h plus f sub a is equal to t times f sub a times y on LT. And my tension will cancel. I can solve this for f sub h, and I'll have that f sub h is equal to f sub a times y on L minus 1. Oh no. And what this will give us is that this relationship tells us that the slope of the f sub h graph, this slope right here, is the opposite of f sub a, because this is the slope relationship right here. And so let me see, I am chasing my, yeah, okay, so ultimately we're trying to find the angle theta here. Yeah, okay, so the slope from C will be the opposite of f sub a, and we can ultimately then plug in the slope from C into this equation right here, along with f sub a, and that will give us the cosine of the angle theta. So to write that out in words, the slope of the graph from C is equal to the opposite of f sub a. And once we know f sub a, we know that cosine of theta from our relationship right here is equal to f sub a on the slope from B, which is equal to the opposite of the slope from C over the slope from B. And that allows us to solve for theta. Yeah, so the argument of the f sub a being the opposite of the slope from graph C is that f sub h is the slope on C multiplied by y over L. And from this relationship right here, we have that. So let's see, we're essentially setting these two equal to each other once you solve the second one for f sub h. And I'll get back to you in just a second, Michael. So yeah, so essentially we just want to relate that the f sub h on y over L is the slope of C, and we have that f sub h is equal to f sub h times y over L minus 1. So we can equate the f sub h's in both of these, and then you'll have that slope of C times L on y is equal to this stuff right here. And equating these two, I will that negative sign. I think I ended up with addition when I should have had f sub h is equal to, oh, there should be a negative sign in here. There should have been a negative sign there. Whew. So yeah, so it's this the negative sign out in front tells us that the slope is equal and opposite, but it's just that another way of looking at this is that f sub h is equal to the opposite of f sub a adjusted by a factor of y over L. Luckily that y over L is on the bottom of this relationship, so that's how we can relate the slope of graph C directly back to f sub a. So to put it, I'm not sure if it'll help to even write out another relationship for it. But yeah, I would definitely say that, again, we're not getting a whole lot of intuition off of this problem because of the just like, I mean, reading the graph in the first place to get the values is not very helpful. The only thing that I think that you really need to be concerned about with this problem going into the exam is just literally the very first step, which was this right here. If you can do this part, that's the only part of this problem that I think is actually important. And Michael asked for part B. We just take the magnitude of the slope of graph C. Part B asks for the magnitude of f sub a, and yeah, that would just be the slope, and then the absolute value of that slope. Yeah, I don't really love this problem. But maybe there's something to it, that maybe there's some pedagogical reason why they would want you to do such a convoluted problem as this that escapes me. But problem number 9 is nicer. Problem number 9 is more in line with the level of physics that I think you should actually be expected to be able to do in this class. Problem number 9, we're back to a plank that is leaned up against like a ledge. So there's your ledge, and here's your plank. The ledge itself has a height of h, and the plank has a length of L, and it's going to be leaning at an angle theta. Okay. Let's see, we're given the length of the plank, we're given its weight, it's hitting the ground. There's a frictionless roller at the top of the wall. So in other words, there's no friction right here, which is good. There will still be a normal force, of course. And the plank is going to remain in equilibrium for any angle. Essentially, they're just giving you an angle theta, and they're asking about the coefficient of static friction between the plank and the ground. Well, let's start there. If I have static friction between the plank and the ground, excuse me, that's going to keep the plank from sliding away from the wall. So that force of friction would have to be directed toward the wall. We'll call that the force of friction. Since we have friction there, there's got to be a normal force as well. Let's go ahead and call that normal force 1. Because as I previously mentioned, there would also be a normal force 2 at the roller. And it's going to be perpendicular to the roller, which is going to make the actual angles there pretty funky. Come on, let me get a 2. Okay, that's supposed to say N2. So ideally, hopefully we can ignore that guy as well. And then the other thing we have is, since there's a weight for the plank, there will be a weight associated with the center of mass of the plank. And we are ultimately asked to solve for the coefficient of static friction with the ground. So let's go ahead and take a look at the the approach to this problem, static equilibrium problem, summing the forces in the x direction, summing the forces in the y direction, and summing the torques. So first of all, the normal force will make an angle with the vertical because of the way that the plank is leaning. I think I said something about like not exactly knowing the angle. It's actually that this angle right here will also be the angle theta that the plank makes with the ground. And the way that we can get there is using similar triangles. So if this is the angle theta, then this is the angle theta as well. These have to be the same angles. And that means that this angle is 90 minus theta, and then this angle is 90 minus theta, which is just theta once again. Okay, so anyway, that angle off the vertical is also theta, which is good news because we want to sum the forces in the x and y direction. In the x direction, the positive x direction, I have my force of friction in the positive x direction. In the negative x direction, I have a component of my normal force N2. So I will subtract that N2, and it'll be sine of that angle theta, and this will be equal to 0. So in other words, the force of friction is equal to N2 sine theta. Next up, go ahead and sum the forces in the y direction. In the positive y direction, I have my normal force N1. I also have the component of my normal force N2, which will be N2 cosine theta. And then in the negative y direction, I have the weight of the plank going down. That'll be equal to 0. And that is a second equation there. If you'd like to rearrange it, well, we'll leave it there for now. The last one that we want to do then is to sum the torques. Now, as I go to sum these torques, as we've done a few times at this point, I pointed out that you generally want to pick a pivot point where you can get rid of the most forces. In this case, it might make sense to set your pivot down here at the bottom. And if you do so, then you could create a torque equation where the only forces that are creating torque are the weight and N2. That sounds like a good deal. And actually, let's go ahead and do that. We'll see how useful that ends up being. But let's go ahead and sum the torques about the bottom. Keeping in mind ultimately that we're looking for the coefficient of static friction. So we need an expression for both N1 and also for the force of friction. Okay, so summing the torques about the bottom, N2 is going to give us a counterclockwise torque. So that'll be a positive torque, and the weight is going to give us clockwise, which will be negative. So for the weight is going to be the distance L over 2. It will be a weight, and I just said it's going to be a negative torque. And then we also need the sine of this angle, which is 90 minus the angle theta that we're using throughout the problem. So sine of the angle between the weight and the plank is the same as cosine of the angle theta that we're given. We actually know it's 70, so you could also just plug in sine of 20 if you'd like. And then we have N2 is providing a positive torque. It is located at a distance that we do not necessarily know. However, we can relate it back to this height h and the angle theta. So to do a quick geometry aside, I have a height of h on a right triangle with angle theta, and I need to find this distance r. I know that r would be, let's see, the sine of theta is equal to h over r, which allows me to say that r is equal to h on sine of theta. So the distance from the pivot point up to that normal force N2 has to be equal to h divided by sine theta. And that's what allows me to write here, when I do my RF, that allows me to write h on sine of theta times N2. I need to do RF sine phi, but the angle between N2 and the plank is 90, so sine phi is sine of 90, which is 1. All right, this is equal to 0. Now, we actually perhaps have solved the problem, rearranging, adding our negative term over to the right-hand side. Well, let's see. Ultimately, what we want to solve for, we would like to have some N2 expression in terms of N1. We could solve for N2 here. We have h, we have theta, we have the length, and we have the weight. Yeah, so we have everything here. We could solve for N2. I guess I'll leave that up to y'all to solve for N2, given the things that you have to plug in. And once we have N2, we can plug that in up here to find our force of friction. And we can also plug it in right here and solve for N1. And then ultimately, you'll use that the force of friction is equal to mu times N1. Take the N1 from this equation and the force of friction from this equation and solve for the mu that you're asked to find in the problem. One note that I'll make is that we chose to set our pivot here when we did the summing of the torques, and we had a simpler equation, which did give us an answer. We could have also chosen to set the pivot, say, up here, and then we would have had a torque equation that would have had the weight torque in it, and would have also had a torque from N1 and also from the force of friction, and you could have solved that way. So there's any number of ways to do it. Since we're in static equilibrium, this thing isn't rotating, we are not confined to a certain pivot point, and different pivot points sometimes will yield different solutions. And in some problems, you actually need to do 2 different pivot points and come up with 2 different equations for the torque, and then solve from there. This is the longest office hours I've had all semester. Sorry for everyone who turns it on at 5 p.m. on Saturday. I do get a chance to see when people watch it, and I know a lot of people will turn it on at like 6 p.m. and see that it's 2 hours long. I will at least try to get it up a little early this week if y'all want to let your friends know to leave a little more time this week for the homework. Okay, problem number HW10, finally. This one is kind of a conceptual problem, so maybe this is a nice last problem to do. You have a stack of blocks that are all sort of like hanging over. And what are we ultimately trying to find? Okay, so each of these blocks has a length of L. Use a different color here. Each of them has a length of L. The distance from the wall to the end of the top block is called H. And then we're asked to solve for each of these little distances, A1, A2, A3, and A4. And we're going to give our answers as an integer times the length of the block. So we just need to find out like how far a block is allowed to overhang. Okay, so here's the long and short of this, the trick to this problem. If each block has a center, right? If I want my block to rest on a table, I need to set it in such a way that the table is underneath the center of mass. If I set my block in such a way that the center of mass hangs over the table, then the block's going to go slipping off the table. That's the whole problem. If you want to test it with your laptop, I'm not liable for what happens to it. But that's the long and short of it. So what that means is with the first block, you just want to start at the top block. The top block can only go out so far as its center of mass remains right at the edge of the block below it. So that means that your A1 at most can only be half of the length of the top block. Once I set that block there, the center of mass of that block and the one below it, since to redraw the picture, you'd have one block with its center right here resting on top of another block with its center right here. Now the center of mass of these two blocks is going to be right in between their individual center of masses, if you look like their vertical center of mass, right? So it would be a quarter of the way from the left edge of the top block, or 3/4 of the way from the bottom edge of the right block, of the bottom block rather. So that means that this distance, the A2, is 1/4 L. And then we just repeat this idea now. So for the next one, where I have 3 of them stacked up on top of each other, I have, let's see, only a quarter. Oh no, put that back. Cool. I have only a quarter of the block that's hanging over. So in this case, I'd have 2/3 of the center of mass of these 3 blocks is located right here, and then 1/3 is located in this point. So that means that the actual center of mass would be 2/3 of the distance between the center and 3/4 of this length right here. So 2/3 of the way there is 2/3 of a half L, which is a third L. Hold on, I missed. It's a third L from the center of the block, which means that, which means that the distance from the edge, because we have, let's see, I'm running out of space here. This distance is 1/3 L. Ultimately, that is the distance from here to here. If this is 1/3 L, then that means that the A3 overhang is 1/6 of an L. And then that center of mass now for the last one. For the last problem now we have the center of mass of these 3 blocks is located at 1/6 of the center of, or rather 1/6 from the right edge of block number 3, which means that block number 2 what was the question? Was this the second one? Let's see, the first one is a half L. The second one was a quarter L. Yeah, A2 is a quarter. You have to split the difference between a half and the center. The third one is a sixth, and then the fourth one is so we have the center. We have 3m essentially. We have 3m that is located at the edge, and we have 1m that's located in the center. So to split the difference between those, that would be 3/4, I should say 3/8 from the center of the block to the point where the center of mass is, which means that the difference here would be a half minus 3/8, which is 1/8 L for this last overhang. And there are probably equations that could be written. I'm just sort of doing this by inspection. You could certainly treat each of these as just like a one-dimensional rod and calculate the torques about the center of mass of each of them in order to find these distances. But yeah, so we have, let's see, this one was a quarter L. So we have a half L, a quarter L, a 6L, and an 1/8 L. So for the last part where you need to find the total overhang distance, you just add all of these together. And I'll leave that up to you. But I am going to go ahead and end the recording because I am out of steam. If you have any questions, let me know. And I'll stick around for just a minute. Yeah, it's no